In this video, I'll be talking about another important application of PN junction, and that's we can use this PN junction for voltage regulation. And and in this format, this PN junction is called as zener diode. So now that's what I'm trying to lay emphasis here on is that these junction diodes can be they can be manufactured for special purposes. And that's other than that of rectification, as we talked about, like that of voltage regulation, light emission, light conduction, solar generation. These could be the probable applications of these junction diodes. Now, this PN junction we can use it as a voltage regulator. Now we want to discuss here this zener diode. Now, what is this zener diode? It's a properly doped PN junction. Properly, so that's the important point. Properly doped PN junction, which works in the breakdown region without damaging itself, and such a kind of PN junction is called as zener diode. This zener diode is also known as breakdown diode, because we exploit this PN junction in its breakdown region. It's designed to operate under reverse bias in the breakdown region. It's mainly used as I said, it's used as voltage regulator. And to differentiate this zener diode, what we show in a symbolic form is something like this. So this is a symbolic presentation of a zener diode. Now, this zener diode, it's fabricated in such a way that both N and P regions of diode are heavily doped, right? Heavily doped. As a result of this, the thickness of its depletion layer or the region that encloses this depletion layer, that becomes very small, of the order of micrometers. I mean, in fact, less than that of a micrometer. So that means nearly less than 10 to the power of -6 meters. Now, a very strong electric field is set up. Is set up across the junction. For instance, let's take an example. If a reverse voltage of 5 volts is applied across a junction, then what would be the estimated electric field at the junction is that will be V by R. Okay, so if I choose V as 5 and the thickness of this depletion layer as 10 to the power of -6, then we're going to have an electric field of the order of 5 into 10 to the power of 6 volt per meter. So this is very strong electric field that is set up across the junction of the diode. And this field that generates at the junction, this is also called as ionizing field, ionized, or I don't know, it's like ionized field. Now, let's go with the volt ampere characteristics of this zener diode, and for that we need a circuit diagram and have a discussion on its VI characteristics. So we have a zener diode. So it's a heavily doped zener diode, and it behaves as the same kind of PN junction in the form of zener diode if we take its forward biasing, if we choose its forward characteristics. So this is my zener diode, and to make it forward biased, this has to be positive. And then let's use some resistance, and then here let's have a milliammeter and connect it like this, and have a voltmeter across this, so that the voltage is measured across this zener diode. So this is the forward biasing, right? So forward biasing, as I said, it behaves exactly same as that of an ordinary PN junction in this case. So if we see here that we'll generally talk about a zener diode made of germanium and a zener diode made of silicon. Okay, these are the basic semiconductor materials. Now, talking about its VI characteristics, we can understand that the VI characteristics of this zener diode can be characterized by simply plotting the output that we will receive in terms of the voltage and current, and then we will have the reverse biased zener diode. So we will have the same situation here. We will have the voltmeter, and then we will have a battery. Here I'll give negative, and then a variable resistance. I should also have a variable resistance, and then a micro ammeter here. So this circuit will refer to the reverse biasing of zener diode, right? Simple. We can characterize them. We can find the relation between voltage and current, and what is the behavior of this reverse biased zener diode. That's the point of contention that we would like to discuss. So if you see this VI characteristics of zener diode, they certainly indicate that a large flow in the circuit, even a small change in the reverse voltage. As we evaluated the previous thing where we saw that the electric field that sets up for taking 5 volts of potential difference, it was nearly 5 into 10 to the power of 6 volt per meter, right? So this much of electric field. So by having a small change in the reverse voltage, in case of zener diode, we are able to have the maximum current. So the large current can flow through this zener diode. In other words, this zener voltage, if I assume that there is V equal to Vz, okay? So V equal to Vz is my zener voltage. So, so I can say that this zener voltage remains almost constant, but large increase in the reverse current. Now, this thing can be interpreted if we plot the characteristics for this zener diode, and if we take for here as we can have an example of say germanium and silicon. So suppose I have to plot the output characteristics. They are same as that of the p-n junction. So this is for this behavior is for germanium, and this behavior is for silicon, and then we have the reverse current, and there is a breakdown, okay, and then we have the reverse current and we have the breakdown, right? So I will assume that this breakdown is this zener breakdown. This is for silicon and for germanium. This is for germanium, right? And this is my this is the current in microamperes here, and here we have current in milliamperes, right? And then this is the forward biasing voltage here. So this is forward biasing, and this is reverse biasing voltage. All right. Now, what is the cause of the sudden breakdown in the reverse characteristics of the zener diode? Now, this reverse current is due to the minority charge carriers. We understand it from p-n junction point of view. If we reverse bias a p-n junction, the current is there is the width of the depletion layer is more, but there is a small magnitude of current, and that is by virtue of what we call as minority charge carriers, right? So in P region we have minority carriers as electrons, and in N region we have minority carriers as holes. Thus, electrons flow from P to N region across the junction, and holes flow from N to P by virtue of the repulsions that these electrons will have with respect to the polarity of the battery that has been connected. Now, the point here is that the p-n junction of this diode, right? We have the depletion layer. Now, when we go for the reverse voltage, when we increase this reverse voltage, and what we see here is to the value of voltage equal to Vz, say for example, in case of germanium. So what happens here is that a very strong electric field of the order of 10 to the power of 6 volt per meter, this much of electric field is set up across this junction, right? And this electric field pulls the electrons from the covalent bonds, which are accelerated from P region to N region. Thus, the flow of these electrons emitted by the electric field, which I told you in the beginning is called as ionizing electric field, because it ionizes the situation here by breaking the bonds. across the junction, that is responsible for this large reverse current at the zener voltage. Now, the next important thing that's linked with this zener diode is that we use this zener diode as a voltage regulator, right? So, in order to demonstrate that thing, if we choose a circuit like this, we have a resistance or and we have a zener diode, and we have a load resistance RL, right? And we connect it like this. Okay, so this is RL. Okay, and we have VZ, and and we want to obtain a stabilized output, so we want constant output. So that should appear here, output. Okay, so let this go like this, and here we have fluctuating voltage as input, fluctuating voltage as input. So, to demonstrate this, so here I take this resistance as RS, and here I take this resistance as RL. Now, a zener diode can be used as a voltage regulator or a voltage stabilizer to provide a constant voltage, right, from a source whose voltage may be fluctuating. This voltage may be fluctuating, and uh, and 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 this voltage, the fluctuating voltage, that is shown here as the input to this zener diode. This zener diode is connected across this fluctuating voltage, across this fluctuating voltage. The fluctuating voltage source through a dropping resistor, can see, of resistance Rs. Okay, here we have a dropping resistance Rs, right? The constant voltage supply is obtained across the load resistance. Now, when the input increases, resistance of the zener diode decreases. Okay, and hence the current through the diode increases to high value. Okay, as a result of this, large voltage drop occurs across this dropping resistance Rs, right? Hence the output voltage across RL is maintained to the desired value. Now, when the input voltage decreases, say for example, then what happens? The current through the diode, the current through this diode also decreases. So now small voltage drop across the diode takes place across the resistance Rs, and the output voltage across RL is maintained at the desired constant value. Now, to understand it, let's take an example. If I take an example of a simple circuit here with R equal to 80 ohms. Okay, and then we have a zener diode. Okay, and then we have a load resistance here, and this load resistance is, say for the sake of argument, it is 100 ohms. Now here in this problem we have VZ. VZ is equal to 5 volts. Am I right? Then and the voltage drop across this R, across the voltage drop across this R, sorry, Rs. is equal to the input voltage. Now, if I choose here the input voltage, say for example, equal to 10 volts, right? So this is my input voltage equal to 10 volts, and this VZ is 5 volts. Now, if I choose this VZ as minus VZ by virtue of convention, because it will be the subtraction of the 10 volts and 5, and that will give me what? That's going to give me the 5 volt. So the voltage across this zener diode is equal to 5 volts. So VZ, as I told, is equal to 5 volts. Now, in order to proceed from here, now I want to calculate the load current. Now, if I want to calculate the load current, that will be equal to IL, suppose that is IL, and that will be equal to VZ, divide by RL, the load resistance. Now, how much is VZ? VZ is 5 volts, okay? Divide by how much is RL? RL is 100 ohms, right? So here we will get 5 into 10 to the power of minus 2 amperes of the current. Hence, the current through R. Now, looking for this current, RS, okay, we are choosing R here. So, hence the current through this R will be how much? Okay, so I must show here current I. Then the current through the zener diode will be like this. So that should be IZ. And here the current through the load is IL. So I can immediately think in terms of the Kirchhoff's law at this junction, right? So if I use the Kirchhoff's law using KCL, what am I going to get? Is this I, this I will be equal to IZ plus IL. Am I right? Yeah. So what is IZ then? IZ will be equal to I minus IL, right? Now, how much is I for the given problem? So the I for the given problem is, how much is that? That's going to be, you can have that 6.25 into 10 to the power of minus 2 minus the current that passes through the load is 5 into 10 to the power of minus 2 amperes. So we can have the subtraction between these two currents, and what am I going to get is 1.25 into 10 to the power of minus 2 ampere. So this will be the current that passes through the zener diode, right? So we have calculated the current that passes through the zener diode as IZ. So that was my problem. I wanted to calculate that current equal to what? So, so this was the important discussion on zener diode, and I hope everybody understands and have a nice time.